this balance.
Hey, we're delighted to have Evgenii Levlev from the University of Minnesota tell us about domain walls and their junctions from N+1 quarks and gluons.
Yeah, so today I will be telling you about some work that we did with Mikhail Shifman and also Shipchenko, who is also a postdoc at and so it's the paper that we did last year. I'll try to convince you that this is exciting, interesting problem. Okay, so this is roughly the plan. So mostly I'll be focused on supersymmetric QCD. N=1 supersymmetric QCD. N=1 means the minimal supersymmetry, and I will be interested in domain walls. I'll explain what these domain walls are, and we will study the effective theory on dealing with these domain walls. And lastly, if we have time, we'll talk about domain wall junctions. Yeah. So when it comes to supersymmetry, there is a lot of machinery and methods also designed for the which heavily use supersymmetry. And one of these notions is the so-called superpotential. So since I'm going to be using this superpotential a lot, I decided to give it a few slides to actually explain, or to specialists just remind what that is. And the idea is very simple and can be explained in this like simplest like two-dimensional model. So consider this QFT in 2D or 1+1D if you want, and there is just like some real scalar field with some potential. In this example, the quark potential. So you know, if you take this potential, for example, be the double potential, so you know that there are kinks interpolating between one vacuum and another. And in this case, note that the potential is non-negative, so it can be written down as a square of another function. In this case, so I take this in a weird form. I'll explain in a moment why I take this function in this form. So I take this potential V as a square of a derivative of another function W, and W is a cubic polynomial in that case. So it's pretty simple. We just like rewriting stuff in a different forms. Well, first thing to note is that minima of the potential are actually given by external points of this W. W will be called superpotential. So the idea is that like since this potential is clearly never turns negative, then minimum of the potential. If you find the zero of the potential, then the zero must be minimum of the potential. Potential can never go negative. But the zero of this potential is zero of this derivative dw over d phi. So these two minima, but the potential actually does turn zero, they correspond to external points of this so-called superpotential W. Okay, so things become more interesting when you write down the energy of your static configuration. So you can consider static configurations with finite energy, which is precisely the king interpolating between these two vacua. And the energy functional, so it's a certain functional, but you can rewrite it as a square plus some a piece which can be actually integrated out. So you see, to complete the square, you need to add this like d phi over dx times dw over d phi, and this product can be actually integrated, right? So this cross term, you can first like sort of like contract dx over dx and do the integral over d phi, and then you can contract d phi with d phi, do the integral of w. So, and this can be like explicitly integrated out. And then if you consider the king, which is the lowest energy configuration in a given topological sector, then this you say that this square bracket actually is zero. This gives you a first order equation for your king. And this finite piece, which can be explicitly integrated out, gives you the energy of this king. So what that tells you is that what that tells you that you don't even need to know the trajectory for your king to know its energy. You just need to know that this trajectory exists, such a particle exists, and then its energy like explicitly given by the difference of the superpotential into vacuum. So here I display some pictures. So this is the sort of like inverted potential, and because the energy configuration looks like a Lagrangian of a one-dimensional particle in inverted potential minus V. So the king travels from one, it interpolates between one minimum and another. And in terms of this superpotential, kings travels from one extremal point to another. So the takeaway message is that when you have this property, this superpotential, then it can actually give you exactly the energy of your topological solution. And you don't even have to know the trajectory. You just need to know that it exists. Of course, on the in this example, on the quantum level, when you consider the quantization of this theory, the king energy receives loop corrections. But in the supersymmetric case, all the loop corrections will actually cancel. Okay. So, are there any questions about this setup? Okay. So now we jump right into the n=1 supersymmetric QCD. So, well, of course, you know very well that ordinary QCD is formulated in terms of gluons and quarks. So gluons are spin-1 particles, quarks are spin-1/2 particles. But when you consider n=1 supersymmetry, you have to like minimally extend it with the inclusion of supersymmetric partners. So for each gluon, you need to include another wide fermion gluina, and for each fermionic quarks, you actually need to add a complex scalar. And it turns out that to like respect the supersymmetry and make it non-anomalous, so each flavor of quarks is a direct fermion, and it can be represented as a pair of wide fermions, and for each of those wide fermions, you need to add a complex scalar. So for each one flavor of fermionic quarks, you actually need two complex scalars in this theory. Yeah. So so these pairs of wide fermions enter in this simplest setup. They enter in a vector-like way. But these wide fermions, which are gluinos, they are chiral, and they lead to breaking of chiral symmetry. So there is a U1 chiral symmetry, which is broken by Evgenii anomaly to Z to N. And this Z to N further broken down spontaneously by gluino condensation to Z2. So Z2 just takes lambda to minus lambda. This symmetry, it's just fermion parity, it's hard to break. And the order parameter for this spontaneous discrete symmetry breaking is the gluino condensate. And there is this gluino condensate is known exactly in this supersymmetric setup. It's just lambda cube. So lambda is it's like a lambda QCD. From parameter in this area. So you see there are like discrete number of vacua. For example, well, I will be focusing today on the gauge group SUN. And if your gauge group is SUN, then you have precisely n vacua in this can be represented by points on a circle in this lambda plane. Right, so, and these vacua are exactly degenerate. So supersymmetry protects their degeneracy. Therefore, you may consider domain walls interpolating between these different vacua. In the simplest case, these domain walls interpolate between neighboring vacua, but you can also consider domain walls which interpolate from one vacuum to not the neighboring one, but in a few vacuum. And the turns out the superpotential that I was talking to you about before. So remember that in that simple pi to the fourth theory in 1 + 1D, you could compute the King energy without knowing the trajectory, just difference of the superpotential between two vacua. So here, the role of the superpotential is actually played by these lambda-lambda condensates, and as soon as you establish the fact of existence of this domain walls, and that you can like immediately write down the energy of this domain wall. So and more like a tension of this domain wall is just given by the difference of the lambda-lambda condensate on both sides of the wall. And you see it has the right dimensions, lambda cubed. So yeah, so and the point is that in supersymmetry, this formula is actually exact on the quantum level as well.
So parametrically, it goes like the tension goes like lambda to a cube.
Yes, exactly. Not just parametric, it's like exactly that. Yes, well, up to some 16 pi, but yeah, but it is exactly lambda cube.
There is no absolute value or anything.
I'm sorry.
This is complex, or just
Yeah. So yeah. I'm sorry. You're right. So this is actually called the central charge, so-called central charge, and the tension is actually absolute value of that central charge. Okay. So and these domain walls can be actually even seen at weak coupling. So the simplest example is consider n equals consider SU2 QCD with one layer of quarks. So you can first of all you can introduce this so-called meson variable, which is basically product of two quark variables contracted. So color indices are contracted. So this is a gauge invariant operator, and in terms of this, you can write down the superpotential in terms of this operator. So this first term here is MQQ tilde is just a master for quarks. The second term is actually instanton generated piece of the potential, more exactly superpotential, which is called affine dizygote potential.
Is there a clear way of understanding why it's case in this way?
The second piece, yeah. So actually did not include that in this presentation. It's quite lengthy subject, but basically there are two ways to obtain it. First, you can consider all the global symmetries of your supersymmetric QCD, including R symmetry, and constrain this superpotential that it is like the only piece that you can add, which respects all the symmetries of the global symmetry. Including this lambda to the 5, but then the numerical coefficient is undetermined. And you can also determine the numerical coefficient, but for that you need to do full instanton computation. So yeah, I actually had one slide which I removed. So you can do one instanton computation and to compute the quark expectation value. So instanton has 4 gluon zero modes and 2 quark zero modes in this area, and you can contract gluon and quark zero modes through the expectation value of scalar quarks through your cover terms. And yeah, and in this way you obtain this superpotential, and you can do the computation, compute the superpotential exactly. Anyway, so first of all, you can find the minima. So as I said, so this is a superpotential, but as you remember, I hope you remember from this slide, remember that minima of the scalar potential are actually given by extremal points of the superpotential. So in QCD, it works like precisely the same way. So you find the extremal values of this superpotential and find the actual vacua of the theory. So you find that there are two vacuas, and moreover, So in this way, you basically determine the vacuum expectation value of your quarks, but then like through certain supersymmetric relation, which is called Caniche relation, you can actually re-express the gluon condensation in terms of the quark condensation. Find out the values of the gluon condensate in this area. And okay, first thing to note is that the quark mass enters in as in a denominator. So when quarks are light, your vacuum expectation values of quarks are actually large, and the sphere is weakly coupled. So the gauge group is like fixed, right? So and the masses of the gluons proportional to the quark left, and when you are at small quark masses, you are at weak coupling. And at weak coupling, you can construct the BPS domain wall, the domain wall trajectories. You can construct them well, pretty reliably. And on the right, I'm showing these two examples of this domain. Also, you have two vacua in this complex plane of meson variable, which is the product of the quark variables. On this plane, you have two vacua, vacuum number one, vacuum number two, and domain walls interpolate from one to another. But you can see that point q equals 0 is actually disfavored by this potential. The particles do not want to go to m equals 0, it's a singularity. So they travel around the origin of this complex planes. They can travel in the upper plane or in the lower plane, which gives you two choices. And there are actually two trajectories for these domain walls. And then you conclude that the domain wall multiplicity is actually 2. So you have just two vacua, and between these fixed two vacua, there can be two inequivalent domain walls interpolating from one to another. So in that simple example with the two-dimensional king in 5 to the 4, there is just one king, but here there can be in fact multiple non-equivalent domain walls interpolating between the same pair of vacua, and these domain walls therefore can form junction. So if you have like domain wall of like type 1 on the top and type 2 on the second, say like then they can meet a junction. And at least in this weak coupling setup. I will tell you later that in supersymmetry, when you have no quarks, you are just in Evgenii area, there can be no junction.
Yeah, did you call only one vacuum or?
I'll tell that in just a second. Yes, I'll tell it in just a second. So here in this slide, I'm just some quick words on generalization of that picture to arbitrary number of colors and flavors. So in that case, you have actually multiple vacua. You don't have just two vacua, you have n vacua of your theory. And then if you pick just two of those vacua, and you consider domain walls interpolating between those vacua, so how do domain wall trajectories look like on the So in fact, now if you have more flavors, your meson matrix is again a product of two quark variable with contracted flavor index, with contracted color indices, not shown, flavor indices appearing free, and it's a matrix. You can it's flavor matrix, you can say, and in terms of its eigenvalues of this matrix, the superpotential in this case will give you a constraint from which we can infer the domain wall trajectories for each domain wall interpolating from one vacuum from vacuum number n to vacuum number n plus k. So through k vacuum. So in this case, it's like k equals 1 is the minimal domain wall, and k equals 3 is the wall shown here. You can actually study the domain wall trajectories in that case as well. And when we had one quark flavor and SU2, we had two domain walls. And in general case, it's actually, it turns out that you can also write down the domain wall multiplicity. And again, between two fixed vacua, there can be multiple domain walls, which are given by this combinatorial coefficient.
Yeah, I got it now.
Yes.
You're the master in the former potential. So you're in the master theory, right?
No, it's a massive theory. It's a massive theory with light quarks. So I start with light. So this is a mass term, and M is not zero. If M is zero, it's actually there is no supersymmetric vacuum in this area. If quarks are massless, so we add quarks which are massive, but for now they are light. And at the end, we will send their mass to infinity. In fact. Yeah. So. Okay. So now. The question that we actually wanted to solve is the following. So these domain walls have been studied by different people. And roughly speaking, this slide summarizes the main results. So, for example, Acharya and Vafa studied the domain walls in pure Young Mills without quarks. And they found out that, okay, there are, again, multiple domain walls interpolating between any fixed pair of vacua. So, and they derive the domain wall multiplicity, and moreover, they derive the effective theory on these domain walls. It turns out it's certainly Chen-Simon's TQFT, but Chen-Simon's topological quantum field theory. But the important detail about that is that they consider domain walls which are actually compactified on a cylinder. So they cannot consider this supersymmetric Young Mills living on R4. They must compactify one of the dimensions, at least the cylinder, or even better the torus. And then they see this multiplicity.
Yes, I don't remember what this example. What it means this notation sub n minus k.
Yeah. So
one is the level of the Chern-Simon or something like that, and the other one.
Yeah. So UK is actually the product of. You can see it as a product of U1 times SUK, right? So this is the level of the non-abelian part, SUK, and this, roughly speaking, the level of the abelian part. Okay, so and this multiplicity is seen as the degeneracy of ground state of this TQFT on the torus. Then that's pure Young Mills, so no quarks. On the other hand, you can study the same theory just with quark flavors, with light quarks. As I said before, at small quark masses, the theory is actually at decoupling. You can study the BPS the domain wall trajectories. And it turns out that the multiplicity of the domain walls is exactly the same as that formula. And the domain wall theory is actually a sigma model. Grassmannian sigma model in this example. Yeah, and then, but the crucial difference between these two theories is that in the latter case, you can have junctions between different domain walls because from the point of view of the effective theory on the wall, the Grassmannian sigma model has like different vacua, and you can consider kinks interpolating between these different vacua, so that in the bulk you can actually study junctions with domain walls, which are in the effective theory seen as kinks of this theory. But there can be no junctions between different ground states with the same TQFT. You can have interfaces between like two different topological quantum field theory that people consider decorated domain walls or yes.
Just understand it because I'm not an expert. I only know the case of the pure Young Mills and the Chern-Simon.
Yeah.
In that case, you have some dualities like k going to n minus k.
Yeah, like
how it acts this domain wall?
Yeah,
should
so,
happen somewhere, right? Because
yeah,
I think if you fix n, but you take k and put it to n minus k.
Exactly.
Yeah.
So it actually the duality you're talking about probably the level rank duality.
Yeah.
Yeah. So in
because you have to change k. This is
k to n minus k.
Yeah.
Yes.
And
And
then fix.
yeah, and in 4D it is actually corresponds to parity. So when you do parity in 4D, it exchanges. So you can see, for example, like this domain wall, you can say it's a K wall which goes to like 1 to 3, or it's a n minus K wall which goes like the long way.
Okay.
And it should be the same domain wall. And parity actually exchanges these two representations of the domain wall. And in the bulk, this is just a parity transformation, but on the domain wall theory, it's a Levlev duality. Yes. So
I see.
this duality
That's trivial in the world.
yeah, so it actually helps to like constrain what the theory actually is,
Okay.
right? But it's sort of it doesn't produce any new results after that. We actually use that duality to like develop the generalization of this theory. But yeah, it's just a parity explanation. Okay, so anyway, so the question that we want to study is this. Suppose I start with the light quarks, then I know that the domain wall theory is the sigma model. I know the multiplicity. Then when I send quark when I increase quark mass and then send it to infinity, at some point I should recover the super young means. I want to believe that when you have quarks of infinite mass, it's actually the same as pure young meals. Right? But in pure young meals, the junctions between different domain walls are impossible. So, but the domain wall multiplicity is the same. So something must happen on the way while you are sending the quark mass to infinity. And in this work, we want to study what precisely what happens. What happens to the theory?
Oh,
Yes.
I really remember this paper from Zohar and Nati, I think also John Gomez, where they study transitions. I mean, they study the phase diagram of some 3D Acharya and QCD.
Yeah.
And I remember seeing these phases showing up on their phase diagram. Do you know how that could be related to the domain wall theory?
Yes. So I might comment on that a bit later. So that's a 3D paper. That's actually
Yes, it's 3D.
yeah. So there are and that problem that we are studying here was also we are not the first to study it.
Mhm.
So other people also did it, and the most difficult, well, one of the difficult things here is that okay. So if you constrain yourself to the framework of the effective theory on the wall,
Yes.
there is some parameter of mass dimension. You
Yes.
can vary this parameter,
Yes.
and you see that there is a phase transition
Yes.
with certain value of that mass parameter. But then the question we wanted to ask: so when we wanted to stick to this parameter n, which is bulk quark
Exactly.
mass.
Yeah.
But how does bulk quark mass correspond to that to your parameter in 3D?
Exactly.
So it is like unclear to say
Mhm.
the least. So and we want to argue that the phase transition that you see in the domain wall actually corresponds to infinite quark mass.
Mhm.
It's the from point of view of the bulk, it's endpoint phase transition
Mhm.
when m actually equals to infinity. Well, by equals to infinity, I mean like for example, if you use Pauli-Wheeler's equalization, that quark mass then equals to Pauli-Wheeler's regulator mass. Yeah. So yeah, so I know those papers, yeah, and there are like other papers by Benini and others also about this topic, but then they study the 3D aspect of the theory,
Yes.
but then you have somehow connected to the 4D parameters. And
Yes,
that's-
some aspect of those papers are still relevant regardless of the specifics of math.
yeah.
The symmetry properties, anomaly matching.
Indeed, they are, yeah, but at the end of the day, yeah, I think I even use those papers at certain time. Yeah, but at the end, you want to formulate the result in terms of the 4D quark mass, and that's a bit tricky. Okay, so are there any? So that was sort of the setup of the problem, and in the following, I'll be actually telling you how we approach solving. So are there any questions?
Yes, about something you mentioned. So in the second case, when the mass is small, you said that you can understand the junctions between the domain walls within the sigma model, right?
Yes.
What do they become when you go to this pure, pure supermodels?
Yes. So
The GKF.
yeah. So
Do they
So
become
actually,
gluons?
yeah. So it will turn out that when you send quark mass to infinity, the sigma model sort of becomes TQFT in a sense, and the junction sort of become infinitely greater.
But
So-
do they give rise to like topological topological defects within the TQFT, or they become trivial?
So the hypothesis is that they actually become Wilson lines, which you can insert in this TQFT.
So they do become
So
anchors.
that is the hypothesis. We didn't actually check this. Yeah. But
But what,
the
what
impression is that yes.
But there's a way you can figure out, for example, the representation of Wilson lines, starting from the domain walls, which form this junction in this bottom.
Yes, in principle, you should be able to do it. But well, I mean, like it's just like a guess at this
see.
point.
But as for example, there's a sensory check like this representation are going to be truncated from the transaminase perspective. Do you see that feature or the from the bottom description?
So we haven't given it much thought. We might discuss this later. Right. So at small quark, when you introduce quarks with small mass, your theory is weakly coupled. But then, like if you actually increase your quark mass and send it to infinity, theory becomes strongly coupled. Then, but you have to do some other approximation to actually compute something. So the only thing actually well in your control is the domain wall tension. You know the formula for the domain wall tension exactly, thanks to the supersymmetry. But like beyond that, it becomes a bit shaky and compute. So the stuff that we did is to consider again circle compactification. So roughly speaking, this is what happens. So to consider, well, first of all, start with the Euclidean version of your SQCD, living on R4, and compactify one of the dimensions. Well, let's say we will call it a time dimension. Of course, in Euclidean theory, it doesn't matter what's time dimension, but for the sake of argument, let's say that we compactify that time dimension, null space dimension are free. And also you do the compactification in a supersymmetric way. So it's not a thermal compactification that you do different periodicity conditions for boson deformants. All the fields are periodic, otherwise you will break supersymmetry. And if you now do a small circle compactification, so your theory is R3 process 1, whereas 1 is small. Then the last component, or fourth component of the gauge field becomes an adjoint scalar in this effective 3D theory. And this adjoint scalar actually hits the gauge group and breaks it to its abelian torque, maximal torque. Right, because yeah. So the remaining three components of the gauge field can actually be dualized to a scalar, and there is a simple relation. So F mu. So mu and nu are now 3D indices which run like 1 to 3. So epsilon tensor, Levi-Civita tensor has 3 indices as well, and the 3 remaining components of a vector field can be now dualized to scalars. In fact, the periodic scalar, and moreover, since you have adjoint fixing, so you started with non-abelian theory, but which is broken down to abelian theory by an adjoint field, you have two Polyakov monopoles in this theory. But it's not quite the ordinary Polyakov monopoles. In 4D, 3D monopoles, so they look like instantons, right? So a monopole in 4D would have a word line, but in 3D EFT, it's actually a point-like object. So you can think of it as a, so remember, we did the circle compactification. We sort of compactify what we call time direction. And 4D monopole or the warp length of the 4D monopole gets wrapped around this compact dimension, and then it becomes a point-like object in 3D. And this monopole generates a superpotential. So if you know Polyakov confinement or vortices and PKT phase transition, it's basically the same thing. So in Polyakov confinement, you know, the instanton monopoles generate cosine potential for the scalar field. Well, this is the just exponential potential, roughly speaking, here the same thing happens. So this monopoles generate, well, in this case, superpotential. And sigma is a, well, superfield, which is, for me, for now, it will be most important that slowest component is just this scalar, a complex scalar comprised of the two scalars that we see so above. So this adjoint scalar, which comes from the gauge field, from force component of the gauge field, and this scalar, which comes from the remaining three components of the gauge field, they get assembled together in one complex scalar, and the potential is exponential in this complex scalar. So, as I mentioned, this gamma is the scalar gamma is periodic, and it enters within imaginary unit here. So the most natural variable is exponential of that, actually. So the most natural variables are these y's, which are called monopole moduli, and for the arbitrary gauge groups, these are just expressed through roots of this gauge group. So these are just technical details which are not particularly important. The important thing is that each monopole now has its own parameter, and the superpotential which this monopole generates. So, as I said, it's exponential type potential, but now we introduce variables which are exponential themselves, so that the potential actually becomes just sum of these y's. Yeah. So in case of gauge group SUN is broken down to UN to n-1, and there is a n-1 corresponding monopole for each of those U1, one monopole for each of those U1. That's the full Polyakov monopole. These are called fundamental monopoles. But due to this nature of our theory that on the microscopic level it's actually 4D, it's one of the dimensions is periodic, there is one extra monopole which is called the Kaluza-Klein monopole, KK monopole. So there are n monopoles and variables in total, and the superpotential is, roughly speaking, a sum of these monopole variables with a constraint. With the constraint that the product of this monopole variable is one. Yeah, so again, okay, as soon as you write down a superpotential for a theory, you can find extremal points of the superpotential, and you infer the vacua. You find that there are indeed n vacua which precisely correspond to those n chiral vacua in the 4D SQCD or 4D supercontinuous theory, and therefore, well, you can study the domain walls and interpolating between this vacua in terms of these y's as well. Yeah, so the story is pretty similar to what I showed in the QCD. So, for example, well, we start with this constraint, and you ask yourself, like, how many domain wall trajectories do I have if I pick a certain pair of vacua? So you pick a pair of vacua, you study like possible windings of your module in the complex plane. So module can wind counterclockwise or clockwise, and they must the domain wall trajectories must be, of course, consistent with superpotential, and you find out that the only consistent trajectory is that when you have a certain number of moduli winding one way, the rest of them wind another way. And that's again technical details, but at the end of the day, which that gives you is the multiplicity of the domain wall trajectories. And this multiplicity is exactly what has been derived previously by, for example, Acharya and Vafa for this domain wall. Okay, but this is actually also known results which have been derived before us. So what we did is to generalize it to the introduction of quarks. So, and here the story is very similar to, say, superconductors. So you know that, like, if you have ordinary superconductor, you have Cooper press, which are electrically charged particles. You have condensation of these electric charges, which in turn leads to confinement of magnetic charges. So if you imagine putting monopole and anti-monopole in the bulk of the superconductor, so their charges cannot be screened because the condensate is electric charge conductor. But instead, the magnetic flux, which flows from monopole to anti-monopole, gets compressed in a thin tube. So the same thing happens in, for example, type 2 superconductors. If you try to apply a strong enough transverse magnetic field, strong enough magnetic field through a thin superconductor plate, you have this abricose vortices, which is precisely the domain, the magnetic flux compressed in thin tubes in the bulk of the superconductor. So condensation of electric charges leads to confinement of magnetic charges. All right, so electric charges can screen other electric charges, but it cannot screen magnetic charges, and magnetic charges become confined. So exactly the same thing happens in this super QCD setup. Roughly speaking, in this 3D effective theory, we have monopoles. But when you start, if you start with the pure superconductors without quarks, you just have monopoles and monopole generated potential. But if you do introduce quarks, say you introduce like a certain number of flavors, quarks become electric charges in this 3D EFT, and they actually do end up getting some non-zero expectation values, and that leads to confinement of monopoles. So if you turns out if you introduce F flavors of quarks, then F plus 1 monopoles actually become confined, and this monopole moduli, which were sort of like free variables, they now, so these monopoles in 3D now become these like chains of F plus 1 monopoles, and they act as a single monopole variable. So this affects the superpotential, so I will skip the technical details, but essentially when you introduce F flavors of quarks, you introduce F extra complex degrees of freedom, but then F degrees of freedom actually also like disappear from the theory because you have confinement of some monopole moduli which were degrees of freedom before, but now they're confined and do not show up in at low energies. And so overall, your number of degrees of freedom is unchanged. So you can find some degrees of freedom, but bring the same number of quark degrees of freedom. And the superpotential is modified, but in a very controlled way. So again, as soon as you write down the superpotential, you also can derive the vacua. There are n vacua in this area, which can precisely correspond to the chiral vacua of 4-dimensional QCD. And then you study this new constraint. And again, you ask a question. So what is how many domain wall trajectories do I have?
So the tension is the power of eta. What is the tension difference?
Yeah, so in 3D, the tension is given, yes, by the power of eta, but when you...
But suppose when you take the mass to infinity, so this tension also tends to infinity.
So it's because, yeah, I forgot to mention it, but in 4D, when the bulk is 4D, the domain wall world volume is 3-dimensional. right? So when we do the compactification, we compactify one dimension, and the domain for self-consistency, we require the domain walls also wrap this dimension, so it becomes two-dimensional.
This one, yeah.
Yeah. So and the domain wall tension is now not a dimension 3 parameter number, but dimension 2 number. So when you decompactify, you have to actually divide by L, roughly speaking, and this will render the domain wall tension still finite. Also when you decompactify.
It's like a density of them.
Yeah, and just the domain wall itself that changes dimension also. It all works out. Yeah. So anyway, so we find that so when we count the domain wall trajectories, so now we have flavor moduli coming from the F flavor that we introduced. We also have leftover monopole moduli, which are not confined yet for if you don't introduce, if you introduce small number of flavors. And this both of them contribute to the domain wall tension, to the domain wall multiplicity, and turns out that there is like a new quantum number. Realizing we put a lot of technical details on these slides, too much, but okay, important thing is that the resulting formula for the domain wall tension like precisely reproduces the known results at weak coupling SQCD, and also if you it also is the same as in SQCD without quarks, but like on the microscopic level it's actually splits into different subsectors. When you sum up over all the subsectors, it all matches the known expectation.
Just to be sure, so in this analysis, you're putting the theorem as 1, but you keep the size fixed, correct?
Yeah, you keep the size fixed, but the next slide is what happens when you send size to infinity. But up to this point, the size was small. The size was small, so that the theory is weakly coupled, and you can. So the point of all of this was that you want to send quark mass to infinity, that the theory becomes strongly coupled, but you need to introduce another parameter, which still renders the theory weakly coupled. You do a little computation, and then we want to try to argue what happens when you actually decompactify.
And you don't expect any kind of order of limit issue if you take the decompactifying limit on the circle.
There can be, but I will argue that it doesn't happen. Yeah. So okay, so I will mention briefly this result. So let's okay, now that we derived domain wall multiplicity, for example, we can try to check this formula, and on the way get some new results. So we want to study the effective theory on the domain wall, and in principle, if you know the effective theory on the domain wall, then this effective theory has a certain number of vacua ground states, and the number of these ground states should match precisely the number of domain walls that you have counted from the bulk perspective. So if you in the bulk you see, for example, like 2 domain walls interpolating between a couple of vacua, then the effective theory on the domain wall should also have 2 ground states in principle. But at least you can expect this thing to happen, and if it does happen, then it is a nice check. It helps. So then we asked ourselves the question: okay, what is the effective theory on the domain wall? And roughly speaking, it's the following thing. So first of all, let me again reiterate the known results. Or if you consider SQCD at weak coupling with n quark flavors, then you have UN flavor symmetry in the bulk. And on the domain wall, because some quark flavors have to like wind one way, but other quark flavors have to wind different way, the flavor symmetry is actually gets broken by each particular wall to this subgroup. and the modular space of the domain walls turns out to be well, it is a quotient. Original symmetry over the symmetry that gets expected by this by a particular solution, and it's a Grassmann. So you can say that, and this has been checked in various ways, that the domain walls area in supersymmetric QCD, effective theory, domain wall is actually a Grassmannian signal model. Okay, then you can expect, then you can ask, okay, so I told you before that when you don't have quarks, the effective theory is actually a TQFT. So how does this TQFT appear in this consideration? Okay, and first, if we start with the compactified theory of the small circle, we don't see any TQFT because there are like certain number of quark flavors with their flavor symmetry. There is certain number of these monopole variables with their own sort of like, it's not exactly flavor symmetry, but it's similar. Okay, by the and each particular domain wall breaks the flavor symmetry and breaks that symmetry of monopole to some subgroup, and then modular space is the quotient of the original symmetry by the subgroup. So we get a product of two Grassmannians. So there is no TQFT here, but then the question happens of the, so that's a small circle story, but then what happens when you decompactify, send values to infinity? So nothing but bad happens to quark variables, so you can expect that it's still the same Grassmannian sigma model, and this has been checked for the perspective. But then monopole moduli disappear, because monopole it even exists in this setup because we have an adjoint scalar which appears only when we compactify a small circle. When the circle gets big, this like adjoint scalar sort of returns back to the being the fourth component of the vector field, the gluon vector field. Monopole modulo disappears, and obviously there can be no sigma model left. The sigma model is for monopole modulo. What happens? What does this Grassmannian model comes to? And we want to argue, and this is more of a hand-wavy argument, but we run a few checks and it works out so far. But this even in the presence of quarks, this Grassmannian sigma model does become some TQFT. And in this slide, I provide some argument that this can, like, so examples of this are known, example of this stuff to happen. Like, for example, simplest Grassmannian sigma model, which is the CP sigma model. Well, you know, it can be recast as a gauge theory with the auxiliary gauge field. So if you introduce this A mu gauge field without a kinetic term, if you integrate it out, you actually recover the nonlinear formulation of CP sigma model, but you can also write it down CP Lagrangian, CP sigma model Lagrangian in this quadratic form with the auxiliary V1 gauge field. And if you add to this theory some number of scalars, which well, I'm sorry, not add to this theory. So yeah, so this can be written down for the CP sigma model, and then you can study this theory as V1 Chern-Simons theory plus some number of scalars charged under this V1 with some potential, and you can study two limits. So, for example, if this potential forces this n to have certain vacuum expectation values, then the gauge field becomes massive. You can forget about the Chern-Simons term, and you recover actually this CP sigma model. But in the other limit, when these fields are actually massive themselves and do not develop vacuum expectation value, then you can, if they are heavy, you can integrate them out, and recover Chern-Simons. So this is an example of a theory which is in one limit can look as it is a Chern-Simons theory, but in the other limit it looks like as a sigma model. So we want to argue that similar sort of thing happens in our case, and also like if you start with the Grassmannian sigma model, you can also write it down as a gauge theory with auxiliary gauge field, but then you can write it as a theory of U. So if you consider this Grassmannian with parameters P and P plus Q, then you can write it down as UP gauge theory or UQ gauge theory. In principle, it shouldn't matter. But in the end, if you apply this sort of logical correspondence and try to guess what Chern-Simons comes at the end, so in these two cases, two different Chern-Simons theories come out, and then you might require sort consistency that the answer should be equivalent. And this actually is equivalent to imposing the level rank duality, and that simple consideration more or less uniquely fixes the domain wall theory. You can argue that your sigma model for the monopole moduli becomes actually a Chern-Simons theory, and you know which Chern-Simons theory. So becomes Chern-Simons theory when you decompactify. Yes, and then we check that. So it's actually supersymmetric, obviously Chern-Simons theory, and supersymmetric sigma model. So the proof that when you have quarks, the total domain wall theory is actually a product of the QFT and sigma model, and then you can study the number of vacua in the sigma model, which is given by the Witten index, and this precisely reduces the number of domain walls. And let me skip to this picture, and then I will wrap up. Stop. Okay, so then I come to the final point. So what happens? So as I mentioned previously, okay, so you see that there is like sort of a phase transition on the domain wall, that this sigma model becomes a TQFT, but at which point in terms of the quark mass, in bulk quark mass, does this phase transition happen? And then we draw the following diagram and try to argue that this phase transition actually happens at the end point of infinitely heavy quarks, not at any value of finite quark parameter. And in order to argue that, so let's suppose the opposite. Let's suppose that the phase transition happens at some finite value of this quark mass. And like to be more precise, by the phase transition here, I will mean the following thing. So as I mentioned before, so when you have quarks, you have a flavor symmetry in the bulk, and this Grassmannian sigma model for the flavor moduli arises from the fact that on the wall, this flavor symmetry is broken to a certain subgroup. And so flavor, so in other words, flavor symmetry is spontaneously broken by the wall. And multiplicity of this domain wall arises precisely because of that spontaneous breaking. So it can be spontaneously broken in different ways, and we count these ways, and this is the multiplicity of the domain walls. So then so in the bulk, when the bulk theory is R4, in pure super Young-Mills theory, the domain wall theory is Chern-Simons, and you also see multiplicity, the domain of the domain walls when you compactify the torus or cylinder. But when you do not compactify, there is only a single ground state for that TQFT, and you don't see this domain wall multiplicity. So this phase transition, if it happens somewhere, it must correspond to the spontaneous breaking of flavor symmetry on the domain wall. So if flavor symmetry is broken on the wall, then we get this multiplicity of walls, and if it's not broken, it's just a single ground state, then we see only a single wall in the decompactified sphere. And multiplicity arises only when you compactify back. Okay, so this phase transition corresponds to, in other words, to spontaneous breaking of Levlev symmetry on the wall. Okay, so then we made the following argument. So let's consider this plane. So this is on x-axis, it's a quark mass, bulk quark mass, and on the y-axis, it's so L is the is the length of the circle, which we compactify on. So L equals infinity is the original theory, and small L corresponds to higher. So what regions are under control here? So first of all, at small quark masses, we have good control because the theory is at decoupling due to fixing by fundamental matter. Right. So at small circle compactifications, the theory is also under control because of adjoint fixing. Right. And precisely at the point n equals infinity, there is sort of a line which is also well studied, but it is well studied because there is no matter in fundamental representation there, and there are certain like high form symmetry machinery which you can apply there, and a lot of people have studied this theory. There are a lot of results which are more or less reliably known for that as well. Okay, so then we try to argue the following thing. Okay, so our symmetry, the Levlev symmetry, is actually zero forms. So if we had a one form symmetry, one form symmetry can be broken like immediately as soon as you introduce the circle compactification. It can get immediately broken. But generally speaking, zero form symmetry should continue with this phase transition, should continue into a phase transition line on this plane, and that line has to end somewhere. And we suppose that there is only one phase transition point on the x-axis, so that line cannot like get back on that axis. So this line has to end like. There are a few possibilities: 1, 2, 3, 4. And roughly speaking, we argued that like neither of those possibilities actually arises. So possibility 4 is like completely crazy because you have domain wall multiplicity here, but no multiplicity here, and these regions cannot be smoothly connected, roughly speaking. And the domain walls 1, 2, and 3 are excluded because they must come into the regions which we know very well, and we do not see any phase transition in those regions. And well, therefore we exclude this line. But therefore, we conclude that this phase transition at finite value of quark mass actually cannot happen. So it's not, of course, like 100% argument, but it's like the best that we came up with. Therefore, we argue that this M star is actually located at the M equals infinity, and this phase transition line actually goes along this pure sim. And this actually is allowed if you like study more carefully what happens in various limits. So this is the only possibility that gets left. And yeah.
What is this M double star?
Yeah, so that I didn't have time to mention. So there is a, so when you have
It's about one form symmetry breaking.
Yeah. So fundamental matter breaks one form symmetry explicitly, but when your quarks are sufficiently heavy, this one form symmetry might arise in the IR.
Yes.
And this M star star is the point where it arises in the IR. Yeah. And
So there are two sort of transitions you're saying, just that they're characterized by different symmetry.
yes, precise. M star star is a one form symmetry. It's transition in the IR. Yeah.
And there's argument that the transition for the one form symmetry has to happen after the zero form breaking.
So no, there is, well, generally speaking, there is no such argument. It's just like in this particular case, we argue that this M star is at infinity.
Yeah.
And it's known generally that M star star is less than infinity. Yeah. Because of some topology, there is such thing as called as topological persistence, that if you break one form symmetry, but only slightly, due to its topological nature, it still survives up to some point. It does not get destroyed immediately. Yeah, here. But then if you on top of fundamental matter, you also do the circle compactification, then it actually will get destroyed immediately. It does not continue as a line, the transition line in this way.
And is that because the multiple operators?
It's so that actually I don't know that well. It's so Shichen, who is also a co-author of that paper, he's a specialist on the function symmetries. He says that this is so. I believed him. Yeah.
I mean, once you
It's
put on a
the-
circle, it becomes a mixture of a zero form and a
Yeah,
one
it's
form
a-
with the perspective.
Oh yeah. That's right. Yes. So you can you can keep you can actually do such a setup that the zero form part is still a good symmetry, but it's not the one that we need for strings. Yeah. So yeah, the one form symmetry, one form part, I think is still killed immediately. Yeah. Anyway, so let me. Now let me skip the junctions part and come to the conclusions. So yeah, so there is this there was this question about the domain walls and chiral symmetry between different chiral symmetry breaking vacua in this area. At intermediate values of quark masses, but this theory is strongly coupled, and I think like we sorted this out, and I didn't have time to explain, but actually we also studied the junctions of the multiple domain walls in this area, and there was a few papers, like for example by Gayotto and others, which studied these domain wall junctions in pure Young Mills. So in pure Young Mills with no quarks, junctions between two walls are impossible, but you can form junctions between multiple walls, like that, for example. And then there is a CFT living on the junctions here, and we generalize the proposal for the theory of the junction to the case with quarks. Yeah, which was not known before. It's a certain CFT times a two-dimensional sigma model, and
Is that a typo? I mean, the level is the same for the numerator and denominator.
here, yeah. So it's a cassette model.
I know, but so there's no typo. The end is
No, there's no type. Yeah, there is no type. Yeah, so you can see from this formula, if you have a product of two series in the denominator, it's a trivial theory. Its central charge will be zero, which corresponds to the fact that there are no two-wall junctions in pure
That's the QFT.
Yeah, but then you can have three-wall junctions, and it's already not trivial. Yeah. So, well, this is it. I hope this was at least mildly interesting. Thank you for your attention.
With these domain walls, sorry, like are these stable, or how do I think about these like cosmologically? Or?
Yeah, so they are not very interesting from cosmological perspective because due to supersymmetry, so we have a number of discrete vacua, and supersymmetry protects their degeneracy. They're exactly degenerate, so the domain wall are eternal. They're exactly stable, right? So if you break SUSY slightly, right, then you can have a splitting between this vacua, and then the domain walls will be unstable, and you can study what happens with those, the dynamics and all that. This story about the stable.
This junctions here, these are supersymmetric.
Yeah, they are in fact n equals to supersymmetric, and it's also another fact that they people have had to mention. Yeah.
0,2.
0,2, yes.
0,2.
So it is there is another interesting thing here. So in the bulk, in 4D, you have n equals 1 supersymmetry, so 4 supercharges. So naturally, you would expect that domain walls would be 1/2 BPS, so 2 supercharges, and junction would be a quarter BPS, 1 supercharge. But turns out that on the domain walls and junctions, SUSY is enhanced. So this sigma model is a Kählerian sigma model.
Is it what sigma?
Kähler sigma model.
Mhm.
It has a Kähler target space, which means in practice that when you have two real supercharges on the wall, they are enhanced to two complex supercharges automatically, at least on the two derivative level in the, so you can call it accidental symmetric enhancement. And the effective theory on the wall is actually n equals to supersymmetric for supercharges. And the junction theory, it's, you would naively expect that it would be 0,1, but it's actually 0,2. So, and we also confirm that from
That's special about this particular cosets.
yes, that's yeah, yes. Yeah, so if in this course you introduce 0,1 SUSY, but it actually automatically enhances to 0.
Okay.
So